All right, now we will continue our computation. We're done with the weld metal capacity of these welded connections. Now we'll solve for the base metal capacity. Solving for the uh, let's say the base metal capacity. Okay, so our base metal capacity is just simply the minimum of the two limit states, which is the shear yielding and the shear fracture. Here we have 0.6 Fy times the thickness and then the weld length. So of course that's going to be the total weld length, or I guess that's the weld length along the shear only. Okay, I'm not sure, so let's think about it. Now if this one should be I mean should this be our load, then the length that's subjected to shear would only be this longitudinal weld length, and this one is not in shear. This would be in tension, right? So I guess um, I think we'll just use this length along the shear line, because this one would be in tension and should be computed differently, I guess. But anyways, for us here, just for computation's sake, we'll just use this length along the shear plane only. Because anyways, if you include this length, then you will have a much larger value of this resistance, or this capacity. But it would be safe if we could just, I think, okay, it's just my opinion, I think it would be safe if we could just assume it this way. I have to check it with the code, but for now let's just assume that the, the length would only correspond to this length along the shear plane. Okay, so that's W sub L, I mean WL. And the other condition is 0.6 Fu times T times the, um, that's the same, weld length um, along the longitudinal. Okay, so now our thickness, if you recall, we have a thickness of 18 mm, and our longitudinal weld length is 300. That's the total of 300. Okay, so now let's substitute the values. We have 0.6, our Fy is 250 megapascals, so this one should be in millimeter. So 18 times 300, 18 times 300, and this one is 0.6 times the Fu of 400. I think we're still missing something, but later on we can just add that 18 times 300. Okay, so we're actually missing this reduction factor. We should multiply this to their corresponding reduction factor. For this shear yielding, we have, if I remember it correctly, I think that's 1.0, and this one is 0.75. Okay, so now let's do the math. That's 0.6 times 250 times 18 times 300 divided by 1000. That's just 810 kilonewton, and this one 0.6 times 400, that's 972 kilonewtons. Okay, so therefore the the design capacity is simply the minimum of the weld metal capacity, which is 633.75, and this value. So the minimum here is 810. Okay, so therefore the design capacity is 630.75 kilonewtons. Okay, so now let's solve, or let's check the code requirements. This is number 5. So checking code requirements. Okay, so our mean is equal to um, since our thickness is 18 mm, then our you can just refer to table 14-3. That's 6 mm. A mean is equal to 6 mm. A max is, since this is greater than 6 mm, I mean this is our thickness. This is our thickness 18. Since this is greater than the 6 mm, then therefore the minus 2 mm. So that's gonna be 18 minus 2. That's 16 mm. And what we used is 10 mm. So therefore code requirement is met. And for the weld length, the minimum weld length is just 4 times A. So 4 times 10 is equal to 40, and we're having 200 or 100. So therefore code requirement is met. Alright, so now let's review our solution to this sample problem number 2. Now the problem is we we have this situation right here that we have a longitudinal weld length and a transverse weld length, and what we did first is to obtain the informations that are necessary. For example, the A36, the yield strength and ultimate strength, and this one, the yield strength of the electrode. So this one can be obtained from the table. And we just write here our weld size, that's 9 mm, the longitudinal weld length, and the transverse weld length, and the thickness, although you can actually obtain it here. Anyway, moving on now, our second step was to solve for the weld metal capacity. We first solve for the capacity per unit length, because once we have this, then we can just multiply it to our lengths, to whichever lengths. So we substitute the values for this equation, or in this equation, and we obtain a value of 1760.43. That's in Newton per mm. If we multiply that to our weld length, then we'll obtain the nominal capacity of the weld condition here. Now, since we have longitudinal and transverse weld length, then we will use this equation: maximum reduction factor times the maximum of the two conditions. Now, this upper condition is just simply the capacity of the longitudinal plus the capacity along the transverse directions, or the this condition 0.85 of the longitudinal plus 1.5 of the transverse. So since the capacity is just the same, then we can just factor it out, and we factored it here, and we just add the weld length. So that's 300 plus 150, so you obtain 450 mm. Then here in this condition, we just factor out this 1760 Newton per mm, and we just multiply the weld length to 0.85 and then this 150 to 1.5, and we obtain this value. After that, we solve the capacity of the base metal, and since we only have a 36 for both the bar and the plate, the gasket plate, then we can just simply use the minimum thickness of the two, and we just apply these expressions on shear yielding and then shear rupture. Now, just a couple of notes. Since this is in shear, then I think, okay, it's just my opinion right here. I haven't checked it yet, but for now, we'll just use this one. That, of course, since we're dealing with shear, then the ones that we should consider here should be the shear, and this one is in shear. Because this one, it would be in tension, so meaning that we have to evaluate this in tension. I guess there'll also be a checking or equations for tension as well, but since we haven't considered it here, then we'll just use this one. Okay, so we substituted the values, and what we get is 810 and 972. So just take note that once we're solving for the capacity or factored capacity, you should not forget this reduction factor and the value of the reduction factor. This is 1.0, this is 0.75. Okay, and the design capacity is actually the minimum of the limit states, which is 633.75, meaning the failure of the weld metal governs the loading or the loading capacity. So after that, we check the code requirements in the A mean, not the AS mean. I mean, the A mean, the weld size, the minimum weld size is that's 6 mm. That's from table. You just check your thickness and you just compare that to the table. And then for the maximum, A max, since we have a thickness greater than 6 mm, then our equation is T minus 2 mm. We have 16 mm. Now, the code requirement is met since our weld size is 10 mm. And that's in between. Now, for the minimum weld length, we have 40 mm. And we have way longer weld length in the problem.